Okay, so here we have the Borromean rings represented in two different ways, and I will show that it is T3, or the way you'd said before. So consider the tubular neighborhood around each of these, right? And then S3 complement the interior of that. So particularly focus on this one or this one. This image will come in handy in a little bit. So we're going to get this tubular neighborhood. Looks like a torus. And imagine this is the tubular neighborhood that's in the S3, and this is the donut that we're gluing in. So in particular, since we're gluing along a slope of 0, this curve becomes, so this meridian curve becomes one of these longitude curves, right? So in particular, this longitude curve bounds a disk in this part of the manifold. Now, in the unknot example, originally we had a sort of like bubble, but a disk coming up here as well, and that's how we got the circle of spheres, right? Now, and we get a whole circle of these disks, right? If we take this longitude curve and then sort of bring it around the meridian curve here, right? You get this whole circle of spheres in the unknot example. We're still getting it here, except now for each of these meridian curves, I'm going to draw the same thing over here. For each of these meridian curves, actually, I'm just not even going to draw the donut. I'm just going to draw the meridian curve. So this curve is the same as this one, right? And we have this disk sort of that's in here. Not sort of, it is in here. If we look at this particular ring, doesn't matter, just fix a ring, fix this ring. Either the bubble or disk is coming this way or into the page or off to infinity, right? And either way, if you look at how this is structured, the bubble coming up, well, let's say it's coming out this way. Let's look at all the undercrossings here. There's an undercrossing here and an undercrossing here. This disk up, no matter where, will be intersecting this particular tubular region in two places. Similarly, if we go into the page, it'll be intersecting this tubular region in two places. So in either case, when you have this disk that's coming up, there are two of these tubes coming in some way. Right? And you know, these tubes continue, but they don't actually hit this disk. So this is where we're going to get our circle. This is a torus, and I will try to explain why. And in particular, you can get a circle going through this bubble here, but remember the torus is here. So if we just sort of like draw our torus, it will go through this disk here and then through the center of the torus, but this disk isn't really there. So it's just going through the center of the torus and exiting out, completing the circle without hitting the torus twice. But what I want to show is, I'm going to draw these tubes coming in here as well. Right, and you can imagine it here. If you've got a bubble coming up these two tubes, it's going to hit these two tubes here, right? If it's this disk is coming up, it's going to intersect these two. It's a little bit easier to see here because you have both of the undercrossings are for the, actually, hold on. Both of these undercrossings are the same disk, and both of the overcrossings are the same unknot, right? So you're going to hit the same tube either way. And this will give us the hole that's in the torus. And I will show that it's a torus by finding two closed curves on the surface that you can, well, they're closed, so they're homotopic to some sort of circle, that's fine. And these curves cannot be shrunk down to a point, nor can they be shrunk into each other, so they're not homotopic. And if you basically get a circle of circles. So you're going to get a circle of circles in this shape, and then you can take this circle and go around, and you're going to get the torus every single time you go around this donut. So you're getting this circle of tori, which in the torus itself is the circle of circles. So we sort of have to see what's happening here when this disk intersects this region, right? Because it's hitting here and going in to the glued donut. So imagine that this is that donut, right? These are both orange. So it's hitting along a meridian, right? It might be tilted, that doesn't matter. So it's going to be similar to a longitude curve here, right? And we're going to have a second longitude curve actually in it as well, because it's hitting the same tubular region twice that we've removed from S3. So there's sort of a circular annulus plane that is in it. So if you take a curve here, let's say it starts at this point here on the boundary of this disk, we go up and around and we go in here, we'll be at this point of the boundary. We can go across to this other point, let's say here, right? Because these are representing two different curves. And then we can come back down. Actually, this is on the back side. And then we can sort of come back down on the front side to somewhere here, where I'm going to say this part of the disk, and then you cross through, now you're in here, back to here. And this is going to be one of your circles, right, that generates the torus. Your second one, well, I'll draw one of them. This is going to be another one of your circles. It's kind of easy to, well, not easy to see, but to make the circles clear, since this is a disk, sort of take the points that are antipodal. Similarly, take the points that are antipodal here, right? You can assign 1 point here, one point here. You can take this and go all the way around, and you're going to get different circles that go all the way around. So you'll be getting a circle of circles. Similarly, you could go around the other circle with this circle here, right? If you could shrink it in to where it eventually becomes the boundary of either one of these, and then you sort of have this circle on this bubble part of the disk, and then eventually you can bring it along here. It intersects the disk, and this circle is only ever intersecting it once is the key, right? These circles only intersect each other once, which is the property we want on a torus. And then you're bringing these disks around. It'll go around here, and then eventually you can come back out of this disk with this circle, travel up here, hug this, and you're on the other side of this. This one's a little bit more tricky to see, but this particular circle of circles is a little bit easier. And there's no way to deform this circle into the other one, because you can't break out of this. There's no way to turn this in such a way that you're getting out. Similarly, you can't, once you're on this plane, you can't end up going through two of them again. That's just not how, the circle won't work that way. Because, I mean, you could move the circle to hitting part of this, but you would just be traveling along like the boundary here, right? Since you'd be entering and exiting the same place, you'd just be doing something like that. And we're trying to keep a regular circle here, or I don't know how to describe it, but these curves can't be changed into each other. They can't be shrunk to a point, because there's always, at least for this particular curve, they're always going to be sort of around these holes or boundaries, and you're never going to be able to shrink it to a point. And you can't, similarly, you can't shrink this one to a point, because you can't escape these tubes. I mean, it's basically, these are similar to the meridian curves that are going through the torus, right? Because you can't, it's going through the hole. You can't escape it, whereas this one is similar to the longitude curves that aren't like bounding the hole, or that aren't, these are like, this particular one here is like these one, and this doesn't really help, but yeah, it's the longitude curves, whereas this one is a meridian curve of the torus. And this is a two manifold, right? Because it's just shallow here. So this is in fact a torus. And to answer your question explicitly, okay, we have a torus here. You could even take the great circle, so this line that goes off to infinity, this vertical line, just shoot it down through this bubble, right? It's going to hit here. It's going to go through the hole of the torus, not hit this disc, right? Because this disc is in the surgery donut, right? So you're only going to intersect the torus once with this circle. And you could do that for every single one of these and get your 3 tori, but I think what you can see here is a little bit stronger, because if you take this and bring it around, right? So say we have this, I don't know, pink or orange, hard to tell. You can bring this blue circle or longitude curve along this meridian curve, and you're going to get a torus every time, because you'll be essentially getting different discs around here. So you'll always be bounding a disc here, and you'll always be getting this bubble up. If we're thinking here, you're going to get a bubble up that's going to hit this particular tubular region twice, or you'll get a bubble into the blackboard that's hitting this one twice. So either way, you're getting a torus. So you're getting the circle of tori, which is precisely T3.